Alright, in case you want to see it again, or just in case you missed it the first time, the fundamental theorem of calculus. I'm going to assume that most of you watching this video have seen this before, so I'm going to start with this idea that if we have a graph, I'm going to use, just like at the very beginning we motivated our study of derivatives with physics, I'm going to do that here too. So let's say we have a graph of velocity versus time, where velocity could be measured, say, in meters per second, and time could be measured in, oh, not meters, my goodness, in seconds. And let's say we have some graph that looks like this. Well, what is the slope of this graph? The slope of this graph would be rise over run. We know it's a derivative, right? But slope would be rise over run. So the units would be the units of rise over the units of run, which would be meters per second, or meters per second squared if you want. And we know that that is acceleration, right? So in this case, slope has a real meaning. The slope of a velocity time graph is acceleration. And you notice here that what is the mathematical operation that you do to find slope? Slope is really division, right? Now, if we wanted to find the area under a velocity versus time graph, well, the area under this would be, if we think about it as like a Riemann sum, maybe something like that, the area of all these things, however we divide this up, it's units, this unit times this unit, right? The area of all our little rectangles, it would be these heights, meters per second, times these seconds. So the area units would be meters per second times seconds, which would be, the seconds would cancel, so we'd get meters. And we're going to learn, this is one of the great applications of this. What is this giving us in meters? It tells us the displacement, or how far this thing, the difference between where it is here at the end of the time interval and where it was here at the beginning of this time interval. So it gives us displacement. Again, in physics this has a real meaning. But what I want you to notice here is, how do you find slope? You divide. How do you find area? Length times width of all the little rectangles. So area is multiplication, right? To find slope, you divide. To find area, you multiply. And we know that since the very beginning of math for you, as soon as you learned how to multiply, then you learned how to divide after that, because these two things are inverse operations of each other, right? Multiplying and dividing are really like two sides of the same mathematical coin, if you want, two sides of the same operation. You want to multiply, you want to get back to where you started, you divide, and vice versa. So these two things are opposite to each other, right? And then going back to here, that must mean, in some very important sense, that slope and area are somehow very intimately related, that they are opposite of each other. And that's what the fundamental theorem does for us. It gives us a way of really nailing down that relationship and showing that that is in fact true. So here we go. We're going to make a graph, nice big graph of a function. I'll call this the f function. And we're going to define an area function. And instead of taking the area from A to B, we're going to take the area from A to some unknown place, x. So the area function would be equal to, and maybe we'll call it like the area. So the area of this function up to x would be a function of x, and that's where the variable would show up. And then this is that kind of weird, sometimes confusing thing here. I'm going to say that this is f of t dt, and the reason that we put the t here is because x is already being used as a variable. So I'm using t. It doesn't really matter what letter you use there as long as you don't use x, because we've already used x. This is sometimes called a dummy variable because we're really just waiting for the x's to come along so that they can come in here, right? The only reason we're not using x here is because we've already used it here. And you know, a function, whatever you want to call the things that you're plugging in, I mean, they're x values, right? So f of x, f of t, f of z, f of whatever letter you want to put there, it's the same function. The important thing is the name of the function, that it's the f function, right? So there's your area function. And then we want to figure out, well, what's the derivative of the area function? So how do we find the derivative of the area function? The derivative, let's call it area prime of x, or if you wanted, you could call it d dx of the area function, right? That's like our derivative operator. That means take the derivative of whatever's in here. When we don't know, when we come across some new kind of function, like an area function, for example, we go back to the definition of the derivative. So the limit as h approaches 0 of f of x plus h. Now my f is the area function, so what does this look like if I plug in x plus h? Let's see, it would look like a to x plus h, f of t dt, minus f of x all over h. Right, now I'm going to go back to that picture for a minute and say, let's say I draw in here. Let's say that this is that little distance h. So this right here, this would be x plus h. So now thinking about what we know about areas, the area from a to x plus h, that would be this area, right, all the way to the far right edge. That is a sort of picture interpretation of what this is, the area from a to x plus h. And I'm going to subtract the area from a to x. So that would be, let's try to do it in a different direction here. That would be this area that only goes up to here, right? So if I take this area from a to x plus h and I subtract the area from a to x, then I would just have this area of this little strip, right? So this is equal to the limit as h approaches 0. This would just give me the area of the little strip x to x plus h of f of t dt all over h. Right? So that's this area here of that little skinny strip. And this is the part where I have to try to convince you that as the h goes to 0, that this little strip will become more and more, no matter how steep this is, as h goes to 0, it becomes more and more and more and more like a rectangle. Right? And as h approaches 0, we could say that it does actually, in fact, approach being a rectangle. And the dimensions of this rectangle, it would be h wide times f of x tall. Right? This would be the height of the rectangle, the value of the function at x. So it's like a rectangle with this area. So as the limit as h approaches 0 of this, that becomes more and more like a rectangle. It has an area. So I'm replacing this expression, which is the area of the strip, saying, well, that's just the area of this rectangle, right? H times f of x over h. And look at that. That's what we always wanted to happen in these limit problems. We want the h to cancel out, and the h is gone now, and as h approaches 0, well, there's no h's in that, so it's just f of x. Boom. That is the fundamental theorem of calculus, and that's what we call part 1 of the fundamental theorem. So again, let's recap that. The area here of this, well, the derivative of that area function is just f of x. The derivative of this area function is just f of x. So let's write down that result. FTC part 1 says that the derivative of this area function from a to x, f of t dt, we use the t's, that's just a dummy variable, is equal to f of x. And I want you to try to understand this in the sense that we are talking about here, that this dividing and multiplying, these are inverse operations, right? So what happens if you have an area function and then you take the derivative of it? Well, that's like what happens if you multiply and then immediately you divide. You get back to where you started, whatever you started with. So these two things, the derivative and the area here, they cancel each other out, and you just get the function that was inside, the f function. So that is telling us, in fact, that taking the derivative and finding the area, those things are, in fact, inverse operations of each other. And that is a powerful thing. Now, the fundamental theorem part 2, we could say this. Let me just remind you here that if we have some function, like the derivative of some function, dy dx, is equal to, let's say, 3x squared. I'd use that as an example. Well, if the derivative of some function is 3x squared, what might the original function have been? We've talked about this idea before, right? What is this the derivative of? Well, 3x squared is the derivative of x cubed, right? But the only thing is that when we take a derivative, if there had been a number here, like plus 3 or plus 4 or minus 7 or whatever you want, that would have disappeared. So in fact, the function that 3x squared is the derivative of, it's not just y equals x cubed. It's y equals x cubed plus any number. Any number could have shown up here. So it's like there's a whole family of functions that could be shifted up or down, which doesn't change the slope, right? If you just move function up a little bit, the slopes are all still the same. So we call this with the plus c here, we call this the general antiderivative, right? So we took the antiderivative of that. Okay, now I'm going to do that to this, right? I'm going to say here, I'm going to take the antiderivative of both sides of this. Well, if that would undo this, right? If I take the antiderivative of this side, it would undo the derivative part. So I'm going to take the antiderivative of FTC part 1. And that will give me the antiderivative of this derivative, just gives me my area function back again. And then the antiderivative of this, well, I don't know what this is. I don't know if it's 3x squared or sine x or could be anything, right? So I'm going to use the common convention that the antiderivative of lowercase f, we're going to call that capital F. But I don't know what that number might be, right? So this is just some antiderivative. It could be any of them. Antiderivative of f of x. Right? So if f of x was 3x squared, it could be x cubed, right? And then I put the plus c in there just to cover, so I could have all the different possibilities there. Right? And now, let's say, well, maybe I could try to figure out what this c is. So if I could know, if there was some value I could plug in for x and know what the c was, then maybe I could figure out what the c was. And the only number here that I really know absolutely for sure, no matter what the f of x function is, the only number I know for sure that I could plug in here and know what it would be a, right? What's the area from a to a? Well, the area from a to a, that's the area from here to here. There is no area, right? You haven't gone anywhere. So it's like a rectangle that has a 0 width. So we know that the area from A to A of f of t, oh my goodness, I made a terrible mistake here. This should be an x here. Sorry. Right, some antiderivative of f of x. That wouldn't be that t in there. That would be back to x's, right? It would be back to the, don't need the dummy variable here. Sorry about that. So that means the area from A to A of this, well, when I plug in, whatever I plug in here gets plugged in here, right? A plus c. But I know that this is 0, right? The area from A to A, any function is just going to be 0. So f of A plus c, so c is equal to negative big F of A, which brings me back to my function here. Now I know what the c is, so A to x of f of t dt is equal to big F of x minus, now I know what the c is, right, minus big F of A. And then, well, I can plug in something else for the, I mean, this is true, but I could plug in another number, like let's say I want to know what the area is from A to B. So the area from A to B of F, and notice now that I'm not using an x, now that I've committed to an actual number there, that means I'm not using the x here anymore. It means I don't need to use the dummy variable anymore. If x isn't being used somewhere else, I can use that there. And now I'm plugging in a b here, so that means I have to plug in a b here for this x also. F of b minus big F of A. And this is the FTC part 2. And if you want my opinion about this, this is pretty exciting that we have demonstrated here that derivative and area just cancel each other out and you get the original function that was inside there. But this is really mind-blowing because of what we can do with this. This means that if you want to find the area under some function, f of x, from a to b, all you need to do is find an antiderivative of this, any antiderivative, right? This is just some antiderivative, and plug in b and subtract what you get when you plug in a, and you get your area. Now, if it seems distressing to you that this could be any antiderivative, remember, whatever antiderivative we picked, if this had the plus c on it, minus this thing would have the same plus c. So whatever the plus c is, it would get canceled out in this operation. You'd have like plus 17 here, minus, and then you'd be subtracting the same thing. So it does not matter what the plus c is. And of course, if you get to choose what the c is, what are you going to choose the c to be? Well, how about 0? That's the easiest one to deal with, right? This is the fundamental theorem part 2. Fundamental theorem part 1 is super, super important. Fundamental theorem part 2 is super, super useful. So, let me go ahead and let's talk about some of the things you can do with that now. So a few quick examples. Do first an example of how you could use fundamental theorem part 1. Say, what is the derivative of the function of 1 to x of t cubed minus the sine of t dt? Well, derivative and area, those things cancel each other out. So what do I get? I just get the function that's inside. But this, the x kind of drops in here. Once I actually do this, once they cancel out, I don't need the dummy variable in here anymore. So what's the derivative of this area function? It's just x cubed minus sine x. That's it. The derivative, area, they cancel each other out. And the one trick is that what if up here, what if it's not just an x? Let's just use the same function here. Well, then this thing, if you think about what's happening here, when I take this derivative, this x squared is the thing that's going to drop in to these. So it would be the x squared gets dropped into the t cubed. But remember, we're taking a derivative, so the rule that we need to remember that applies here is the chain rule. When I drop this x squared in here, it does just drop into where the t was, right? And it'd be x squared cubed, but I have to multiply by the derivative of what's inside. And I would like you to understand that as just the chain rule, right? We're just using the chain rule. And then minus the sine of t and x squared, that's the thing that's dropping in there. And, oops, no it's not. Just kidding. It's x squared, right? And then I multiply by the derivative of what's inside. So this is going to drop into wherever the t's are, and if it's not just an x, you have to multiply by the derivative of what's inside. And then last trick is, notice in both of these, as per the fundamental theorem, if that's just a number on the bottom, it doesn't matter what the number is. We just get the function that's inside. But what if it's something else, like an x on the bottom? What if we want the area from x to x squared, and we want to take the derivative of that? What then? Well, then we basically just use the rules of breaking up intervals. So let me just make a quick sketch here. If we had the area from, let's say, 1 to 3, some function f of x dx, well, that's the same. Let's say we pick a number like 0 that's below both of these. that would be equal to the area from 0 to 3, f of x dx, minus the area from 0 to 1, f of x dx. Right? We've already done problems like this. We're just kind of manipulating areas. And in fact, we used that same idea here. Right? We said this area from a to x plus h minus this area. Well, that's just the area from here to here. Right? So it's like our 0, 1, and our 3. Same idea. So we can apply that here. So this is really like the derivative of the function from a number, like say 0, it doesn't matter what the number is, to x squared. So that would just be the same as this, which would be x to the 6th times 2x, I guess 2x to the 7th if you want to simplify that, minus sine of x squared times 2x, and then minus that whole thing, minus the area from 0 to this. So that would be this one dropping in now. So that would be x cubed minus the sine of x. Right? So if it's a number to x, it's just the function that's inside. If it's a number to some function of x, that function drops in and we just use the chain rule. And if it's functions top and bottom, then this drops in with the chain rule, if necessary, minus this drops in with the chain rule, if necessary. But here it was just an x, so I'm going to multiply by the derivative inside of what's inside. Fine, it's just 1, right? So that's cool. That's a good kind of problem to understand. And then, so this is kind of an example. That's how you can use fundamental theorem part 1. And then part 2, and say, well, what's the area from 0 to 3 under the parabola x squared dx? I think this is one that you might have approximated in a recent homework assignment. So how do we do this? Fundamental theorem part 2 says all you need is any antiderivative of this. So an antiderivative of x squared is x cubed over 3 plus whatever you want. So I'm going to pick the whatever I want to be 0. Notation-wise, I put this in square brackets and I put the 0 to 3 here to remind myself that I still have to plug these in. Then I plug the 3 in. That's 3 cubed over 3 minus whatever I get when I plug the 0 in. And that's 9. That's pretty amazing. That's a way of finding, I mean, this is a parabola. That is not a shape that we know areas about from geometry, right? And here, this gives us a very nice way of doing that. You also, in the homework, approximated the area from 0 to pi under the sine function, right? So that'd be like the area under the first bump of the sine function there. So let's see here. An antiderivative of the sine function. You be careful with your signs with positives and negatives. The we want to know, like, what would I have to take the derivative of to get sine? Well, if I took the derivative of cosine, that would give me negative sine. So the antiderivative of sine is negative cosine, right? It's the opposite signs of what you get when you take derivatives. Right? Think about that for a minute if you need to. And then I'm going to do that, and I need to plug in pi. So negative cosine of pi minus, careful again with signs here, minus negative cosine of 0. Right? I have a negative in here, so negative cosine of pi minus negative cosine of 0. So a negative sign there. The cosine of pi is negative 1. Minus minus, that's plus. The cosine of 0 is 1. Negative negative 1, that's 1 plus 1 is 2. So that's another fairly mind-blowing thing, in my opinion. What's the area under the first bump of the sine curve? It's not some weird pi kind of number or some other irrational number. It's exactly 2. That area is exactly 2. And if you look back at your approximation sheet that you did not too long ago, you'll see that all of your approximations using Riemann sums and trapezoids and whatnot, they were all in fact very close to 2. But you want to know the exact area? It's 2. You don't believe me? Go ask Wolfram alpha, and you'll find out that it is. And that's by Fundamental Theorem of Calculus, Part 2. And then I'll just do one more quick example for you, just so you know when we see this. Now, what looks different about that problem? You might think that maybe it's getting late and I have just forgotten something, but I intentionally left off the numbers here and here. So what does it mean when we write this? Well, for a very, very good reason that I think you probably understand now, we're going to use this notation to mean find the antiderivative. And if I don't put numbers here, we call this an indefinite integral. In other words, we're looking for not the actual area from here to here. We just want to know what's the antiderivative of this. And it makes sense that we would recycle this notation because that's exactly what you have to do to evaluate these things. You have to find the antiderivative. So we say, well, you know what? We'll just use this symbol to mean that too, and we won't put numbers there when we just mean find the antiderivative. So you scratch your head for a second and think, do I know a function that has a derivative equal to 1 over x? Yes, you do. It's the natural log function. And it's actually the natural log absolute value of x, right? Plus c. So if there's no numbers here, we're just finding an antiderivative, but don't forget this, right? That is called the constant of integration. That's very important. So there you go, the fundamental theorem of calculus. It's pretty amazing, and it's the bridge between the first half, say, or so, of a calculus course and the second half or so of a calculus course. So this is the bridge between finding derivatives, which has been our focus so far up to this point, and doing what is called integration or integral calculus. How are those things connected? By the fundamental theorem of calculus. They are opposite operations to each other. Finding a derivative is like dividing, right? It's like slope. Slope is dividing, rise over run. Finding an area, that's like multiplying, length times width. And just like multiplication and division are opposite operations or inverse operations, so are taking derivatives and finding areas. They undo each other, right? They complete each other, if you want to cast it in a more sort of romantic way. But maybe that's going too far.